Good morning, students. So we are studying about the first chapter, solid state, and in last class we have done about the closed pack structures. In 3 dimension you have got three types of packing. One is called simple cubic packing, one is called cubic closed packing, and one is called hexagonal closed packing, HCP. And when we do the 3-dimensional structure, then after placing the second layer, you know there are two types of voids generated. Some voids are called tetrahedral void and some voids are called octahedral void. When a triangular void is covered by one particle, that type of voids are called tetrahedral void. And when two triangular void combination takes place, then combination of two triangular void is said to be the octahedral void. Now, what about the location of tetrahedral and octahedral void? I mean, in unit cell, where is the position where the voids are present? Suppose this is one of the unit cell. This is your unit cell. In this unit cell, this is a simple cubic unit cell. In this unit cell, as you know, from one corner to another corner, this line is called edge of the cube. There are 12 edges in a cube, and each edge contains a center. This is called center of edge, like this. These are the center of edges. Since there are 12 edges, you will get 12 center like this. Every edge center contain one octahedral void. I mean, these are the position of octahedral void. I mean, octahedral voids are present at the center of all edges, and one octahedral void is present at the center of the cube. So this is the position of octahedral void. Octahedral voids are present at the center of the edges, and one octahedral void is present at the body center. This is the location of octahedral void. I mean, octahedral void are present at the center of edges and at body center. Body center means the center of the cube. This is the position of octahedral void. And tetrahedral voids are present. Tetrahedral voids are present in the body diagonal. In the body diagonal. Each body diagonal contain two tetrahedral voids. Each body diagonal contain two tetrahedral voids at 1/4 distance. This is the position of tetrahedral void. As you know, this is one of the backside corner and this is one of the front side corner. When you draw a line from the backside corner to this front side corner, then the line comes through the body. I mean through the center of the cube. This is called body diagonal. I mean, when you draw a line from one corner to another corner through the body, then that diagonal is called body diagonal. And in a cube, you can draw 4 body diagonal. Every body diagonal, suppose this is one of the body diagonal, every body diagonal contain two tetrahedral voids at 1/4 distance like this. If one tetrahedral void is present here, then another tetrahedral void will be present here. So this is the position of your tetrahedral void. Since you can draw 4 body diagonal, I mean you will get 8 octahedral void inside the unit cell, because one body diagonal contain two tetrahedral void. There are 4 body diagonal you can draw inside the cube. That's why you will get 8 tetrahedral void. And what about the octahedral void? Octahedral voids are present at the center of edges. How many edges? There are 12 edges. So 12 octahedral void you will get, and one octahedral void you will get at the center of the cube. I mean at the body center. That means total number of octahedral void you will get 13 in the unit cell. So octahedral voids are present at the center of the edges and at the body center, and tetrahedral voids are present at the body diagonal, and each body diagonal contain each body diagonal contain 2 tetrahedral void at 1/4 distance. So you should know about the position of the voids, where the tetrahedral voids are present, where the octahedral voids are present. Now this is another topic which is called packing efficiency. This is very important for exam. You have to find out the packing efficiency. Actually, packing efficiency means nothing. It is the percentage of the total space occupied by the particles. As you know, particles are spherical, and due to spherical shape of particle, when you arrange the particles, some gap will be present in between the particles. That is why you cannot occupy all the spaces present. Some vacant spaces will be present inside the total space. So how much percentage of the total space occupied by the particle, that is called packing efficiency. Suppose I have given a box, and inside the box you have to arrange the marbles. So when you arrange the marbles, some gap will be present in between the marbles, and that is why you cannot occupy all the spaces present inside the box. So how much space occupied by the marbles, that is called the packing efficiency. And to determine packing efficiency, first time you determine the total volume, then you determine the volume of the particle, then you can find out how much volume occupied by the particle. I mean, you can find out the packing efficiency. So packing efficiency means nothing. It is the percentage of total space occupied by the particles. Now we will determine the packing efficiency for face-centered cubic, for body-centered cubic, for simple cubic. So individually we will find out the packing efficiency. First time we will determine the packing efficiency for face-centered cubic. As you know, in face-centered cubic, the particles are present at the corners and at the center of the faces. So if the particles are present in that way, then how many percentage of the total space occupied by the particle, that you can determine. So number one, we will determine for CCP or FCC. You know, FCC means face-centered cubic and CCP means cubic close packing. Cubic close packing and face-centered cubic, the arrangement is same. So FCC is said to be CCP also, arrangements are same. So to find out the packing efficiency, let the edge length of the unit cell is a centimeter. I mean, this is the unit cell. If this is the unit cell, the length from one corner to another corner, this length we have considered as a centimeter, and that is called the edge length. Let the edge length of the unit cell is a centimeter. So since edge length is a, therefore volume of the unit cell, length into breadth into height. Since the edge length is a, so volume will be a cube centimeter cube. Now for FCC, for face-centered cubic, you have got R is equal A by 2 root 2. Already you have got this relation. This is the relation between radius of particle and the edge length of the unit cell. The radius is equal edge length by 2 root 2. Already you have got this relation. That means you can write A is equal 2 root 2 R. So in terms of radius, volume of the unit cell, as you have got volume of the unit cell is a cube means 2 root 2 R whole cube. 2 root 2 R whole cube means 2 cube means 8. 8 into 2, I mean you will get 16 R cube. Sorry, 16 root 2 R cube. 16 root 2 R cube. So this is the volume of the unit cell. Since in FCC, one unit cell contain 4 particles, one unit cell contain 4 particles. Already you have determined how many particles present per unit cell in lattice. For FCC you will get 4 particles in one unit cell. For BCC you will get 2 particles in one unit cell. For simple cubic you will get 1 particle only. So since FCC contain 4 particles, therefore volume of 4 particles, this is equal, as you know particles are spherical, and what is the formula to determine volume of sphere? 4 by 3 pi r cube. Since there are 4 particles, so 4 into 4 by 3 pi r cube. Ultimately you can write 16 by 3 pi r cube. This is the volume of the particle. So you have determined volume of unit cell, you have determined volume of particle. So now you can determine the packing efficiency for CCP. So therefore packing efficiency, P is equal, P means packing efficiency, this is equal volume of particle divided by volume of unit cell whole thing multiplied by 100. So volume of particle you have got 16 by 3 pi r cube, 16 by 3 pi r cube. Volume of unit cell you have got 16 root 2 r cube into 100. So r cube will be cancelled. You know the pi value is 3.14, root 2 value is 1.41. When you put all these value, after calculation you will get 74%. This is called packing efficiency. I mean 74% of the total space occupied by the particles, which is called packing efficiency, and the another 26% it will remain as vacant space. As you know, particles are spherical. Due to spherical shape, you cannot occupy the all spaces present inside the cube. So that is why some vacant spaces will be there. If it is simple cubic, then 74% of the total space occupied by the particle and 20% will remain as the vacant space.